Thank you. So this is work based on this paper on the archive with my collaborators Rolando Soma and Davide Orsuki, both of whom are in the audience today. Okay, so the previous talk actually did most of the introduction to this problem for me, but for the benefit of people just arriving, let me quickly define the problem we are trying to solve. I'm sure you are all familiar with this linear systems problem where we are given a matrix A, n by n, and a vector B of n dimension n, and our task is to solve the equation A times x equals B for the unknown x. And the best known general purpose algorithm, classical algorithm for this is the conjugate gradient method, and its complexity scales linearly with the dimension n. So for this talk, I will assume this dimension is exponentially large. And Harrow, Hessedem, and Lloyd have formulated the quantum version of this problem, where the task is not outputting all the entries of this exponentially large vector, but rather preparing a quantum state such that the amplitudes of the state are proportional to the entries of the components of the vector x. So in this talk, I will describe you algorithms for a slight variation of this problem, where the goal is not to output a pure state anymore, but rather a mixed state, rho sub x, such that this mixed state is close in trace distance to the state x. Okay, and this version of the problem is adequate for all practical purposes, because the goal is, in this quantum linear system problem, only to compute some expectation values of observables in the state x. And this can be done with equal precision with this mixed state as it can be done with a pure state that's epsilon close. Okay, so I will make some standard assumptions, such as requiring that A is invertible, otherwise we will be doing the pseudo-inverse, that the norm of A is bounded by 1, and that A is Hermitian. These can be easily lifted. And finally, I will assume that A is a sparse matrix, meaning it has at most D non-zero entries per row. So to analyze the complexity of the algorithms for this problem in the query model, let's define an oracle A that runs in time t sub A and outputs the non-zero entries of this matrix A and their indices, just like here. And also I will assume that there's a unitary U sub B that prepares a quantum state, B, that is defined in a way analogous to the way that I defined X. And it runs in time T sub B. So given these definitions, HHL algorithm solves this problem with complexity given by this expression. So here, let me emphasize that the dependence, explicit dependence on the dimension goes with log of n, and this is where the potential speedup, exponential speedup comes from. As long as the condition number, which is the ratio of the largest to the smallest eigenvalue of the matrix, and the circuits that prepare B are also scaled like logarithmically in n. So the HHL algorithm, as was described by Andreas in the previous talk, uses these three subroutines: Hamiltonian simulation with the Hamiltonian A, phase estimation, and amplitude amplification. And they achieve a kappa square scaling. And in that paper, they showed that the optimal scaling is linear in kappa. So this linear scaling was achieved by Ambainis. So this square goes to linear by introducing a very sophisticated, complex subroutine called variable time amplitude amplification. And this requires a lot of ancillary qubits and operations conditioned on these ancillary qubits. And finally, Childs, Kothari, and Soma were able to improve the precision dependence to become polylog in 1 over epsilon by replacing the phase estimation by linear combination of unitaries. But they still had to use variable time amplitude amplification to get the optimal scaling in kappa. So here the tilde note indicates I'm ignoring polylogarithmic factors. So in this talk, I will tell you about a quantum algorithm that has a very different flavor than these previous approaches and solves this problem with this complexity. So almost optimal in kappa, but not optimal in the precision. But we will be able to do this by using only one subroutine, just Hamiltonian simulation, and only at most 2 more additional ancillary qubits beyond what is needed by the Hamiltonian simulation. Okay, and just to the point that our algorithm is very simple, within 2 weeks of posting our results, Van et al. Was able to implement this algorithm in a 4-qubit NMR quantum device to solve an 8x8 quantum linear systems problem, which, to the best of my knowledge, is the largest instance of this problem solved to date. Yeah, very impressive 8x8. So some applications of this problem are determining the quality of least squares fit, analyzing large sparse electrical networks, solving systems of differential equations, estimating kitting time of Markov chains, or computing electromagnetic scattering cross-sections of targets. So for this last application, there was a very detailed analysis of the resources needed for the HHL algorithm. And in the regime where the quantum complexity is supposed to take over, one is the estimates are really high for the number of qubits and the number of gates that are needed. So one way to bring these down is, of course, to improve the subroutines and to do more careful analysis. And a different approach is just to look for a altogether different algorithm for this problem, which is the topic of my talk. So before I move on, let me just mention some caveats about this potentially speed-ups for this problem using quantum computers. So even for these applications I've shown you, there are a number of assumptions that must be met in order to get a quantum speed-up. So these include efficient preparation of the state B, that the condition number itself doesn't scale with the problem size, dimension of the linear system, and that the quantity actually we are interested in is an expectation value of an operator. So for these reasons, a lot of the shown quantum speedups are typically polynomial, and more of the caveats can be found in this commentary by Scott Aronson. Okay, so although the final algorithm does not use adiabatic evolutions, it was our inspiration to come up with this algorithm. So, and it's most easily described in this setting. So let me briefly review adiabatic quantum computing. Here the goal is to, here we start with an easy Hamiltonian, and we prepare its ground state, which we assume can be efficiently prepared. And then we design a final Hamiltonian such that its ground state encodes the output of the desired output of the computation. And then our goal is to slowly interpolate between the initial Hamiltonian and the final Hamiltonian, and in the process prepare the desired output from the initial state. And the adiabatic theorem says that we can do this as long as we do this interpolation slow enough. And slow enough usually means that in a time that goes like 1 over the gap square, where the gap is the energy difference between the ground state and the first excited state. And we care about the minimum gap. Okay, so let's try to find an algorithm for the linear system problem in this spirit. So first I will show you only a method that works for positive A, and it trivially generalizes to more generic matrices. So let's define a projector that projects onto this space orthogonal to the one spanned by the vector B, by the state B. So this here is my linear system of equations. AX has to be proportional to B. If I multiply both sides of this equation by this projector, the right-hand side gives me trivially 0. So now I define this product of these two operators as B, which is not a Hermitian operator. So I multiply it by its Hermitian conjugate to get a Hermitian operator, which will be my final Hamiltonian. So this is by construction Hermitian. It's manifestly positive semi-definite. And from this equation, I know that X is an eigenstate with eigenvalue 0. As a result, X must be a ground state of this Hamiltonian. And with a little bit more thinking, you can see that it's actually a unique ground state of this Hamiltonian. Okay, so we found a simple-looking Hamiltonian whose ground state is X. So next we want to find an interpolation to an even simpler Hamiltonian whose ground state is also simple to prepare. So to this end, we define an interpolation, A of S, that interpolates between the identity matrix and A itself. And we get a parameterized family of Hamiltonians by replacing A with A of S in the definition of the final Hamiltonian. And using the similar arguments as in the previous slide, it's easy to see that now this state is the unique ground state of this Hamiltonian for all values of S. So what this tells me is that for each value of S, the ground state of H of S actually encodes the solution of the linear system problem where the matrix is replaced by this interpolation between identity and A. So this is a very intuitive structure now to the problem. And if you look at the condition number of this matrix as a function of S, we see that for most values of S, this is a very well conditioned matrix, and towards the end of the protocol, the condition number picks up. So this is what a adiabatic algorithm now for this problem would look like. We would start with the initial Hamiltonian, which is simply the projection onto the orthogonal space of B. And we would start with the initial state B, which we assumed is can be prepared efficiently. And we would change S from 0 to 1 and obtain the state X. Okay, so with the adiabatic algorithm or variance of it, the complexity is determined, the time complexity is determined by how the gap behaves. And in order to bound the gap, we write it as the Hamiltonian as sum of two terms and use Weyl inequality to bound the gap. So Weyl inequality says that if a matrix is the sum of two matrices, then the eigenvalues of the matrix can be lower bounded by the eigenvalue of corresponding eigenvalue of the other matrix and the smallest eigenvalue of the second matrix. So pictorially it looks like this. We are adding the smallest eigenvalue x1 to all eigenvalues y, and we still have to be smaller than or equal to the eigenvalues of z. So by simply choosing the first term here in the Hamiltonian to be x and the second term to be y, we get a very lower bound on the spectral gap. And this lower bound starts very large at the initial value of the parameter s, and it slowly decreases to its final value 1 over kappa square. This is consistent with the condition number decreasing. So the gap getting closer, or at least the bound on the gap getting closer, indicates the problem is getting harder and harder. Okay, so it's a nice property of the adiabatic evolutions that the complexity only depends on the gap. So if you want to improve upon the algorithm, we just need to focus on this one quantity. We just need to amplify the gap. And one method to do this is called spectral gap amplification. So let me remind you how our previous Hamiltonian looked like. Now we can define a different Hamiltonian, which is H prime of S, where we added an ancilla qubit. And this ancilla qubit allowed us to obtain a Hermitian operator by basically using only one power of B. And when we look at the square of this operator, we see that the square is block diagonal. And in the top block corresponding to the ancilla being in the 0 state, I recover the original Hamiltonian from the previous slides. So in this sense, the H prime acts like the square root of H in a loose sense. This can be made more rigorous by looking at the spectrum of the two Hamiltonians. So for each eigenvalue of H of S, lambda, there are two eigenvalues of H prime that have values plus and minus square root of lambda. Except for the eigen state with eigenvalue 0, it gets mapped to two states, degenerate states, in the middle of the spectrum now, not anymore ground state. And one of these two degenerate states has actually the solution to the linear system problem embedded there. So, and the gap between this subspace and the others is amplified quadratically. So we get a quadratic improvement on the gap. Of course, you might be worried that now there's a degeneracy, but there are no transition matrix elements between these two states. So the only relevant gap is the square root of delta. And you might also be worried that maybe in moving from one Hamiltonian to the other one, we made it much more complex to simulate. But this is also not the case. They both have similar complexity of simulation. So we don't lose anything. We gained a quadratic improvement on the gap. So now our bound on the gap is given by 1 over the condition number as opposed to the condition number square. And now the corresponding adiabatic algorithm would look like something like this. We would start in the state where the ancilla is in the 0 state and the rest in the state B. And by slowly changing S, we would get the final state in which, again, the ancilla is in the 0 state. Okay, and in the general case, the previous, by just replacing the previous definition of A of S with this one, where we added another ancilla qubit, we can get, we can handle non-positive matrices. And we need this ancilla qubit because otherwise, somewhere along the way, A of S becomes non-invertible. Okay, so the eigenpath of these Hamiltonians can be traversed using many different methods. One method being the adiabatic evolution. And in that case, the time that we have to take to do the interpolation scales like 1 over the gap square. And using the bounds on the gap that I showed you in the previous slides, we can see that the corresponding time complexities would scale like kappa to the 4 and kappa square for each Hamiltonians. So the point is that using the known bounds for adiabatic quantum computing, we cannot prove an optimal scaling, which goes like linearly in kappa. That's why we are looking at different approaches, one for eigenpath traversal. So one is randomization method, which is a variant of adiabatic quantum computing. So the bottom line is that the time complexity of the randomization method is given by this formula, where L is the path length of the eigenstate that the eigenstate traverses in the, during the interpolation. But important to notice is that the dependence on the gap is quadratically better. And for this problem, we are able to show that actually the path length is only scales like log kappa. So when I put the bounds on the gap into this expression, I get two time complexities. One that scales almost quadratically in kappa, the other one almost linearly in kappa. So this will be the basis of our algorithm that achieves optimal scaling. So let me tell you how the randomization method works a little bit, or at least give you a sense of how it works. So it's based on two ideas. The first one is that imperfect measurement. Oh, no, this is the second idea. Okay, the first idea is that we can prepare successive eigenstates of this parameterized Hamiltonian by performing measurements in the energy basis at intervals dense enough so that the corresponding eigenstates have large overlap. And for this, again, for this particular problem, it turns out that we need a number of points at which we want to do the measurements that scales only with log square kappa over epsilon. So we don't need many points. But performing measurements in the energy basis is hard. So this is where the second idea comes in. It just states that imperfect measurements can be simulated by evolving with the Hamiltonian for a random amount of time. So the way this works is that if we write the Hamiltonian in the density matrix in the eigenbasis of the Hamiltonian, when we evolve in time, we see that the off-diagonal elements of the density matrix pick up some phase. And if the evolution time is random, we have to integrate over all these times, meaning all these random phases. And this probability distribution can be chosen such that these random phases all add up to 0, effectively killing the off-diagonal elements of the density matrix, which is what simulates a measurement. Okay, so when working with the randomization method, it's convenient to adopt this so-called natural parameterization, which allows us, by introducing another parameter v that's related to s in this way, which allows us to take equal steps in the parameter v, and as a result we get equal overlap, at least overlap that's bounded by the same constant between successive eigenvalues. And an equal grid on the v scale, of course, corresponds to a discretization on the s-axis that is denser and denser towards the end of the interpolation, which is again corresponds to the fact that the problem gets harder and harder to solve. The wave functions evolve faster and faster towards the end of the iteration. So it turns out the times, the probability distribution for the random times can be chosen uniformly from this interval 0 to 2 pi over the gap in order to achieve enough decoherence and imitate the measurement enough. And the time complexity is given defined as the average time for the total evolution. And note that also the maximum amount of time is also bounded, and it's actually twice this average time. Now I want to highlight some subtleties of this method. In each run of the algorithm, the evolution is actually unitary, meaning that we are actually preparing a pure state. But because the evolution time is random, this pure state is also random. But there is no guarantee that this pure state is actually close to the state X that we are trying to prepare. This is in contrast to adiabatic quantum computing, where we always prepare a pure state that's close. But what is saving the situation is that these random pure states are described, the ensemble of them is described by a mixed state. And it's for this mixed state that we have this guarantee on the trace distance being epsilon close. So in reality, we will be doing, we will be running the randomized evolutions one at a time, get pure states, compute some expectation value, we prepare new states, and on average, the average that we will obtain will be epsilon close. Okay, so I can tell you what our algorithm is now, put everything together. Given the condition number kappa and some precision epsilon, we define, we pick an integer q of this size, and then also we calculate the step size of the randomization method. This q will tell us how many different Hamiltonians we need to evolve with. Then we will find the corresponding values of S that will tell us which Hamiltonians we are going to evolve with, and sample some random times in this interval. So here the delta star is the lower bound on the gap of the Hamiltonian H. And then we will prepare this state B and act on it with simple time evolutions, with Q different constant Hamiltonians. And the time complexity is given by kappa square log kappa over epsilon. So for the second algorithm, we do pretty much the same thing, use the same interpolations, but now we use the second Hamiltonian H prime. And now the times are sampled from a much smaller interval that's quadratically smaller because the bound on the gap is quadratically smaller. And also the initial state has this ancilla attached in the zero state. And this algorithm has a time scaling that goes like kappa log kappa over epsilon. Okay, so I described you these two algorithms in terms of some evolutions with Hamiltonians. And these Hamiltonians looked very simple. They were easily described by the inputs of the problem. They were products of A, projections onto B, and some simple Pauli operators. But they may not correspond to a physical model. And actually implementation on some device, on some analog device might be not practical. So for this purpose, we studied whether they can be simulated efficiently in a gate-based computer using Hamiltonian simulation methods. So the method we adopted is the one by Berry et al. And this one is based on, this one requires you to write your Hamiltonian as a linear combination of unitaries. So we were able to, so let me just show you the Hamiltonian for the second more efficient algorithm. We were able to write this Hamiltonian as a linear combination of 32 unitaries using a version of Szegedi-Volks. So now this Hamiltonian, the complexity of the Hamiltonian simulation can be measured in terms of how many times these unitaries are applied. And that goes like linear in the total evolution time and the sparsity d. Moreover, in our construction that I don't have time to show, we observe that these unitaries require a constant number of calls to the oracle A and to the unitary that prepares the state B. So the total, and in addition there are some order log and 2-qubit gates. So, and since the average evolution time is given by kappa log kappa over epsilon, by putting it together with these two facts, we obtain the total query complexity that is given by the expression I cited in the beginning of my talk, and which is almost optimal in the condition number. So this is it. This is the entire algorithm. Let me just conclude with some comments. So our algorithm are conceptually simple, and they don't rely on complex subroutines. They only use Hamiltonian simulation. The Hamiltonians involved are easy to describe, and more importantly, they're efficient to simulate. We are using at most 2 additional ancillas beyond what is needed for Hamiltonian simulation. And this is in contrast to previous approaches that achieved the optimal scaling in the condition number that had to use this variable time amplitude amplification, which adds a lot of ancillary qubits and controlled operations to your circuit. But more generally, I think our results emphasize the importance of considering other models of quantum computing, which go beyond gate-based model, in order to discover novel quantum algorithms. And actually, not that many adiabatic-inspired quantum algorithms exist for which speeds up have been proven, at least for non-artificial problems of interest. And so this is one of these cases. And that our work also demonstrates that even for algorithms for which we have very efficient asymptotic scaling algorithms, there's room for improvement. So with this, I'd like to thank you.
So we have plenty of time for questions. From the front.
Okay, so you explained that if you're trying to use the adiabatic algorithm, the time is limited by the 1 over gap squared, and therefore this doesn't work. But then the gap is only very small at the very end. So we know that in some cases, by using a non-linear interpolation schedule, we can recover quadratic speedup. So would that work here?
Yeah, we were not able to find such a schedule. Let me put it this way.
One just there.
Hello?
Oh, but let me also comment on one thing. So if the implementation is going to be on a gate-based digital quantum computer, also the randomization method seems more natural because you perform evolutions with fixed Hamiltonian. So, yeah. Yes.
In the middle, you talk about each run you get a pure state output, and those pure states are not close to the eigenstate, but their average is close to the eigenstate.
Which
But-
is good.
but
By the averages, yes.
the
And
average-
some, yeah.
But if the eigenstate is a pure state, that doesn't sound quite possible. So
Yeah, so let me give you the following example. So there is a finite probability that all the times, evolution times can be 0, sampled to be 0. In which case, the state I will prepare, starting from B, will be identical to B itself. And in general, B will be very different than X. So it's possible that in the one instance of the randomization method, one run of the algorithm, you might get a state that is completely orthogonal to X. So this is possible. But in order to compute any expectation value, you need to run the algorithm many times. And the guarantee that we have is on this kind of expectation values.
does that mean with high probability the output is going to be close to the eigenstate? So the orthogonal output is really low probability even.
Yeah, so the probability of getting those bad states will be small.
Okay,
It
okay.
has to be small, yes.
I see.
There was one question here and then at the front. Or was that question evaporated? No. Here then, at the front.
I just would like to ask about this sampling. So in this slide, you say that you need to sample uniformly at time from 0 to something like 2 pi over the gap. And well, yeah, I understand this, but so on the other slide you had like an upper bound on the gap, which is more natural, I guess. So what happens if your upper bound is like off by say 1.5, then it's like wraps around only 1.5 times? Isn't that a problem, or you maybe you have some?
So you are
logarithm
saying if
over-
my upper bound is very loose, can I get into trouble by running longer? No, I don't think this is an issue. I think you only run into trouble if you. So the type of distributions you can sample from is pretty relaxed actually, and I think the more important point is that you evolve enough times to make sure that you can get these phase cancellations. But I think if you allow more time, that's not an issue as far as I can tell.
We still have time for one or two more questions if there are any.
There's one question back there. All the way back there.
Can you lift your hand high in the air and wait for the microphone? Thanks.
Can't you just detect at the end whether you've missed the correct ground state by doing the phase estimation?
Wait, can you repeat the question?
So like you're trying to stay in that zero energy state, right? So
In the first algorithm, I'm trying to stay in the zero energy eigenstate. In
Yeah.
the second one, yes, I'm still trying to stay in
yeah.
the-
So can't you just detect if you've lost that state by doing phase estimation at the end?
Yeah, you could, but we were trying to avoid phase estimation as well as variable time amplitude amplification.
Oh, you mean just to save on qubits?
But yeah, I don't think you will get any benefit by detecting it because, as I said, yes, you have no guarantee that you prepare a state close to it, but those states don't come with high probability. So you could maybe weed them out by doing phase estimation. But then I don't know if this bound on the trace distance will be still valid.
Okay.
So, yeah, I don't
just
think
thought it might give better scaling with the error. I just thought it might give better scaling with the error if you're actually detecting the errors.
Right. Maybe improve the dependence on
Yeah,
error.
yeah.
That's a possibility. I haven't thought. But yeah,
Okay.
good point.
Okay, we'll maybe have time one more quick question.
Does the adiabatic approach can implement the pseudo-inverse function? The pseudo-inverse, sorry.
Adiabatic approach is what?
Does this adiabatic approach can implement the pseudo-inverse,
Yeah.
the pseudo-inverse of the matrix?
Yeah, so if you have a non-invertible matrix, right, as long as your initial state B doesn't have support on it, it would do the pseudo inverse. If your state B has support on it, it might do something funny in that subspace.
So it works, right?
It works, yeah.
Thank you.
Okay, so let's thank Yigit and all the speakers this session again.